So in today's session, we will explore together convolutional neural networks. And convolutional neural networks are actually very popular. They present the basis of foundational models in especially computer vision. And so we will start by looking at the difference between a fully connected network, or like such as an MLP, and a convolutional neural network. So the first question that we have here is, how and why did CNNs emerge? Okay, so before that we had, beautiful MLPs that are able to classify, for example, images. So if we input this image right here to this network, you guys can see that, we can train different weights and different, layers. And towards the very end of the network, we are able to predict two classes. So let's say, one if there is a cat in the image, and 0 if there is no cat in the image, okay? So we have also seen that deep neural network can be formalized as the learning of what we call is sequential paths. And these paths, they have weights. So from each input node to each output, so we have multiple kinds of paths, and every time you go through this path, we are able to update the weights based on the loss that we want, the target loss that we define and that we want to decrease. Okay, so a change in the loss will enable us to update the weights using the gradient descent formula. Okay, so so here we have also seen that through this, every single path, every single path in the network, we can perform this kind of, a gradient calculation or weight differentiation, and back propagate through these sequential paths and do some sort of, gradient collection from the back of the network all the way to the beginning of the network. So all of these, we have seen them in the previous lectures. Now, one main question here is that, okay, so we have a fully connected network, which means each node here, so each node, let me just remove all these. All right, so each node is actually connected to a set of nodes, right? So all nodes is fully connected to all nodes in the next layer. So this is a fully connected network. So the question that we ask here, what are the pros or what are the disadvantages of such network? When basically would such network fail, or what are the disadvantages of this fully connected network? So there are a few, and here we're going to play a game. And this game, basically, it's a true-false game. So we have here 5 statements, and we're going to look at each of these statements and basically give a false or a true to each one of them. So let's start with the first statement. So what does the first statement say? So fully connected networks, a fully connected network has a notion of nearby pixels and treats a few inputs dependently on others. So what does this sentence mean? So let's think about it. So what this sentence tells us is that if I have, for example, a pixel in this image, right? Okay, inside the cat right here. So this is the pixel xi. Then this pixel will be treated in a way that is dependent on its neighboring pixel, for example, xj. Okay, so these pixels are within the same kind of neighborhood, and in this fully connected network, we are able to capture, pixels within a particular neighborhood. Let's say n of I is the index of the pixel centered, the center of this circle, okay? So if you look here, what actually happens in this network is that every single pixel learns its own weights. So here, if we call this, you know, pixel 1, and these are the hidden layers. So we have W11, W12, and W13. And for another pixel that is neighboring to that one, so XJ here. So this is our XJ, this is XI. Let's call it, you know, like pixel 3 here. So J is equal to 3 for simplicity. So we're going to have W31, W32, and W33. So what do you guys notice? If we take these weights, W11, W12, W13, and the neighboring pixel, W31, W32, and W33. So these are basically, these weights are actually, these vector weights right here are actually different, okay? So which means if we look at this statement, this statement turns out to be actually false. Why is that? Because every time a fully connected network is trained, it treats each pixel independently of its neighboring pixel. So it is learning an independent, okay, mapping of each position or pixel in the image. All right, so of course here you may ask, oh, how did we actually get this, you know, like vector? Of course, we vectorize the image, so we kind of, you know, go through the image pixel by pixel, and we do this kind of horizontal vectorization, and we store the pixel values inside the input layer, okay? Cool. Now, so we can see that this network learns for each pixel a completely independent mapping. So if you think about it, this, you know, path right here, this multipath emerging from this node will be different from this multipath emerging from another node. Whether this node is nearby or far away, the network doesn't really care about that because the network doesn't look at nearby pixels. It doesn't have a sense of locality, okay? So, or localization. It doesn't have a sense of locality or localization. So this is, you know, something that is kind of, you know, it's a drawback of FCNs, because first, an image has what we call a spatial locality, right? So, you know, neighboring pixels, they may have similar statistical attributes, similar intensities. You can see here, this belongs to the background right here, the curtains, and the curtains have the same, you know, kind of pixel values or intensity values, right? So neighborhood in images, spatial neighborhood is very important. So let's look at the second sentence. So what is the second sentence here? Let's read it together. So number 2, so basically permuting pixels, network entries won't affect the network, okay? Is it true or false? So what does that mean? It means that if I permute these, I apply a permutation pi, a random permutation pi to my input data, to my input vector. Okay, so this is the input vector. And I randomly kind of shuffle the nodes right here. So I randomly shuffle them. The question here, will I learn, you know, like, you know, a different, completely different mapping for this, after this shuffling, okay? So will I get also completely different outputs? So it turns out, because of the independence rule, because we have an independence between all pixels, so if you shuffle them, this, you know, learning may not really depend on the learning of the other guy, because there is no constraint here, which means shuffling them will turn out to, you know, may lead to the same performance or behavior of the network. Of course, there will be some changes here in the learned weights, but these are negligible changes, and the overall behavior will be almost the same, okay? So basically, the second here statement is correct. So in a fully connected network, permuting pixels or network entries won't affect the network. So let's look at number 3. So number 3 is if the pixels of train and test images are permuted randomly in the same way, which means if you take, the input data and the output, okay? The train data and the test, and you apply the same random, shuffling. So if I call it pi1, I'm going to apply pi1 here to all images in the same way. So I'm permuting everybody. I'm randomly shuffling all pixels in exactly the same way. So here, the hypothesis is that if they are shuffled or permuted randomly in the same way, the FCN could still be trained with no practical difference, okay? So this is also true, and this is linked to the previous hypothesis. So here we're generalizing to, testing and training data, and because statement 2 is correct, we can derive statement 3, all right? Now let's look at statement 4. What is statement 4? Statement 4 states that shifting the input data to FCN does not cause, for shifting here, it means translating. So if you have a tree, you will translate the tree. So you have a tree right here, you will have, a translation of the tree, of the whole image. So you translate or you shift, horizontally shift the image, okay? So shifting the image does not cause the network to relearn the patterns of pixels corresponding to the target object at each position. All right, now let's think about it. So you take the image of this cat and you shift it a little bit. So once you shift it, you have what this hypothesis is telling us, that after shifting the position, this position, so let's draw, for example, the cat right here. So let's say this is the cat, right? Something like that. Okay, so I shifted my cat over here. So let's say the head is, or maybe I shifted it a bit down. Okay, so that's also shifting, vertical shifting. So if I have the position, this position, let's call it the position xi. Now my shifted position is actually xi plus a delta, which is, for example, we can call it xi prime, right? So what this hypothesis is telling us is that the target, the network, will learn the same patterns at the pixels corresponding to the target object at each position. So basically what it's telling us that at this position, after we actually translate the network, we will have exactly the same mapping here, okay? So remember, in this position xi, I don't have a cat right here. So the cat disappeared, the cat is actually here. So, but this hypothesis is telling us that the network will still learn the same mapping, W1, 2, and 3 at this position xi, independently of the shifting, okay? Invariantly to the shifting. So it doesn't care. It will still identify, the same mapping for this localization, even if we shift the image. So of course, if you guys think about it, this doesn't apply because logically, this pixel right here, which is now xi prime, this should have the mapping or an approximate mapping that is similar to W1, W1, 2, and W1, 3. So this should be at xi prime, okay, the shifted position. So it would not be exactly the same as I said because it's an optimization problem, but it cannot be preserved. So here, this statement, the shifting the input to FCN will lead to learning the same patterns is actually incorrect. So it will actually does not cause the network to relearn. It does cause the network to relearn the patterns of pixels corresponding to the target object at each position. So every time you need to relearn again if you have shifting. So this is this a good property to have in a network? So let me just take this back. Is this a good property to have in a network? Of course not. Why? Because when you take images or pictures, if you want your network to recognize a cat right here, you may have different pictures of cat with different positions. You may have a cat playing. You may have a cat eating. You may have, the cat in different locations of your image. So even if you translate or you shift or you change the position of the cat, the network should be aware that this is a translated version, and I still need to learn a similar mapping of my cat so I can, classify it well. So the problem with this, I mean, even if you shift, the network can still be trained well. You can still minimize the loss. I can still minimize the loss here. But the problem, it is really consuming, because every time you change or you shift the data, the network will need to relearn everything. And this relearning is due to this independence, because these mappings are independent for every single position and every pixel in the input image. Okay, so let's look at number 5. So what is the fifth statement here? So the fifth statement is about the nodes in the FCN layers, or the input and hidden layers. So here the hypothesis is that nodes in a fully connected network, they share weights. Okay, so weight sharing. What does weight sharing mean? It means some nodes may have exactly the same weights. So if we go back to our original notes, so let me do the recoloring again. So lots of colors here, it's getting too crowded, but let's try to simplify. So let's say this is our, here we go. So this is our one node, okay? So the weights of node xj, and we have the weights of nodes xi. So, okay. So the hypothesis states that some nodes, and ideally, of course, like we would want the, similar nodes within the same, nodes in the same, or pixels in the same neighborhood to share similar weights, because they have similar properties. They are very similar. So since they are similar in the intensity or domain, or in the original domain, maybe they should be mapped similarly. They should be transformed or mapped similarly. Okay, similarly. So here, if we say that the network shares weights between some nodes and ideally nearby nodes, it means that, well, these two, the blue and the pink, they will be identical. They will be identical, okay? So identical means they share weights, which means that we map these two entries in an identical way. Okay, so we map them similarly. We use the same transformation to learn, their mapping. Okay, so this is what it means to share weights. It means that some nodes will have identical weights. Actually, if you think about it, if these two nodes right here have identical weights, right? So this node and this node have identical weights. It means if I'm sharing these mappings, actually I'm learning a lot of pairs or subsets of identical mappings, which will reduce the network, right? So here, instead of learning all these sort of mappings here, we have n times n prime, so n times n prime matrix, like a huge weight matrix. We will have a lot of redundancy in the matrix because many weights will be identical. Okay, so we're kind of reducing the problem computationally a little bit, but by sharing these kind of weights. But as you guys can see, so we're going to go back this. Okay, so to our hypotheses, the last one tells us that the network shares weights. Well, is it true or false? It's actually false. Okay, so nodes in FCN layers do not share weights, unfortunately. So you can see now that fully connected networks, they're always fully connected. They do not care about like the nearby pixels. They don't have a sense of locality. Fully connected networks are basically networks that try to learn in an individualistic, egocentric manner, which means I look at each pixel in my image individually, and I don't care about the relationship between, faraway pixels or nearby pixels, okay? So it's self-centered. It just looks at each pixel one at a time and learns how to map each of those. So the problem with that, of course, it comes at a high, with a high computational cost and budget, because you need to learn this mapping for every single pixel, and you don't care about the others. So, individualism comes with a very high cost, which is, the use of a lot of resources. So if you think in a more smarter and like collective manner, you would hypothesize that, well, my network should be smarter at learning or dealing with images, because we have this kind of local similarity between pixels belonging to the same object. So why not stipulate or encourage, these pixels, all of these pixels, to learn the same kind of weights, okay? So this is something that actually inspired the emergence or the design of convolutional neural networks. So let's take it one step at a time and see how these convolutional neural networks have been built, okay? So first, right here, the first question that I want to ask is how can we modify the fully connected network? So let's choose a different color, okay? The fully connected network to meet the following properties in image data. Okay, so the first property is that nearby pixels are statistically related. So we know, for example, if we look at these two pixels, and here I'm gonna call this pixel, this is xi, xj. So if you plot the distribution of this pixel, so which is around this neighborhood, okay, and you take, for example, this neighborhood, and these are actually very close, what do you notice? That these two actually will have similar distribution, okay? So locally for each, local point, we may have similar first intensity values, for example, 108, and here we'll have, for example, 106. So the intensity values are close, okay, because of the locality. We hypothesize that they're, except if you're at the edge, of course, you have a change of intensity, but if you're inside the object, generally, you have this sense of locality where you hypothesize that things will not change a lot, like right here, right here. So everybody's similar to, their nearby pixels or their local neighborhood. So what this tells us that they're statistically related because their, local neighborhoods here are correlated, highly correlated. So they are kind of similar. So there is a correlation in the value, the mean, and the standard deviation within these small, I would say, very small close by neighborhoods, because these guys are close, okay? So now to think about this hypothesis, how can we make a network? How can we, what do we need to transform? What do we need to change in this network to make it satisfy this condition A? Okay, so that's something I want you to think about. Of course, here, the way we're doing the mapping needs to be different. We can't do it completely independently, which means, in a very independent way, where each node learns its own kind of, mapping individually. Okay, to just minimize the ultimate loss, of course, but they're not codependent. So this architecture, this graph right here, the way we connect layers need to be changed. So try to think about it now. So the next condition is the shifting. Okay, so the interpretation of an image should remain stable under geometric transformation. So which means geometric transformation here includes translation. If we, for example, rotate the image, if we scale the image a little bit, okay? So if we do these operations, we apply these geometric operations to the image, we should always be able to recognize that we have a cat. So if we take this cat right here, and the cat, basically, we rotate it, and we give the network a rotated image. So we'll crop it. So this is the rotated cat, right? This is the rotated image. And we compare it, and we should have exactly the same, output, right? So which means that the network will still know or identify this image as a cat. It will interpret it in the same way if we apply any geometric transformation. So mathematically, what does this mean? It's very simple. Mathematically, if we start with f of x, so here we have f of x is the mapping, the network that we apply to the input x, we get the label y. Okay, so this is, we have the image x, the output y. And then if we transform the image, so we apply a transformation to the image t of x. So here this transformation will, transform, rotate, translate our image x. Now, when we apply our network, when we, train our network on the transformed image right here, this is the transformed input, right? We will still get exactly the same output. So we will get y, which is the same label. I mean, like if it's a cat, so it's 1, for example, which is f of x. So this means that f of t of x is equal to f of x. And here we define what we call invariance, mathematical invariance. So here we say that f is actually invariant to transformation t. And this is the definition of the mathematical invariance. All right. So in an ideal network, that solves the problems of this, fully connected network, we would have what we call, locality. All right. And then we will have also something called invariance to transformations. Okay, so network invariance. So here the network is F, okay, to transformation. So these are two properties that we wish to achieve. And here, so the idea here is that, well, how can we actually design a network that allows us to do this thing, to achieve these properties? So one thing you can think about is that we need to transform nearby pixels similarly. So if we have xj is in the neighborhood within the vicinity of xi, then we let the network act on xi and xj similarly, okay, in a similar way. Similarly. So here t is a transformation, but if you think about it, if you transform both of them here, if if we transform pixels similarly, the output also will be transformed similarly, and that's a different type of thing we'll talk about later. But here the idea is that I want to kind of apply the same rule to neighboring pixels. So let's look at that here. So let's start with this example. So we have different things here. All right. So, right. Okay. So in the first example, I'm going to move this right here, guys. Okay, we don't need it from there. All right. So the first idea is that we look at this image, and then what we want to apply the same transformation. Okay, so let's call it here, actually, to not have confusion, let's call it f to xi and xj. So if xj is within the vicinity of xi, so let's put this here, okay? So if this is 1 pixel, So this is, for example, let's call this, I'm just putting things randomly here, xi. This is xj. If these two are actually neighboring pixels, so here I took very big pixels, okay? It means that the mapping that we apply or we learned for xi and xj should be the same. What does that mean? It means that if I'm going to change this, I'm going to remove all of this, right? So let's think about it. Here, I have xi, okay? And here, I have xj. So basically, what this tells us that if I want to use, a sort of a fully connected network, I need to get the same weights, okay? So all of these guys will be identical. All right, so that's one way. So we make the mapping here identical to this mapping. So we stipulate this kind of learning of the same weights. So we can actually model this or plot it differently. So let's look at this together. So if we call this, like a weight mapping, so W here. So what we want actually these two neighboring pixels to share the same mapping W. Okay, so they share exactly the same mapping W over here. All right, so when they share the same mapping, then the outputs, of course, will be different, slightly different, because these have slightly different values, but they have been mapped in the same way. So something in the network needs to kind of be updated. So let's keep going. So how are we going to manifest that? So here, in this case, I'm gonna take, let me copy paste one of these. So copy and paste. All right, so we have that. All right, so in this network, let's look at this network. And let me just zoom so you can see it clearly. So what happens, actually, is that all these, like if we have, for example, 4 neighbors, so this is, these are 4 neighboring pixels. These 4 neighbors, because they are within the same neighborhood, they should be transformed in the same way. So I'm going to learn a mapping here for these, let's call them, first set of neighboring pixels, or for this kind of patch right here, that is 2 by 2. Now, if I move to a different location in the image, all right, these 4 neighboring pixels also should have, so if these are my pixels, right, should share the same mapping. So I'm going to color them differently. And then because they are neighbors, I need to apply to them the same also mapping W. Okay, so all of these guys go into this mapping, and I'm going to call it actually only W, because I'm mapping similarly. I'm sharing the weights. I'm mapping similarly all neighboring pixels. So I'm applying this same mapping function, or let's call it also, we can call it transformation, okay, to neighboring pixels or pixels nearby. So that's the idea. Here, we are applying the same transformation locally to each pixel, so that to each, patch here. So, so this is actually not a bad solution. So what have we done here? If you think about it in this network, first, we have achieved the locality A constraint that we talked about earlier. So right here, nearby pixels are statistically related, so we're treating them similarly. And the thing about transformation, so we'll get to it in a bit, but in this case, you guys can see that first, at least, we're applying the same, we're learning the same transformation for nearby pixels. So the locality is fully, met right here. Good. So now let's move to the next part. So here we use a different, so you may think, okay, you may ask a question right here. You may ask me a question. Why do we actually use the same weight? Does it make sense to use exactly the same transformation for everybody? So which means if I have this, pixel, this, patch right here, I'm gonna map all these guys similarly. Does it make sense to you to map all of them similarly? So if I learn this W, and if my W is not good enough, right? So let's say my W, this shared, weight map. If it's not good, then, basically we'll screw up the loss. We will have also bad prediction of the final labels, right? So everything is connected here, interconnected from, optimization to weight update to bad propagation to performance of the model, etc. So apply the same rule, apply the same rule to everybody, to everybody. So who is everybody here? At each position of in the input data, okay, is kind of reductionist. Okay, don't you think? It's a bit reductionist, which means, well, here I'm going to I'm going to capture only a particular type of mapping and relationship between these. Okay, so if I multiply this by W1, W2, W3, W4, and this turns out to be my unique mapping in this neural network, then basically I'm not taking into account the variation of the properties, statistical properties of these neighborhoods across this image, right? So basically I'm considering everybody similarly in exactly in an identical way, and this may be reductionist. Okay, so it will limit your learning. So that's what it means. Reductionist, it will limit the learning capacity of the network, the learning capacity, which is so important, capacity of the network. Okay, so the capacity here is depicted by the W, the shared W. Now, let's look at a different case and think about how can we possibly change this. Okay, so here, as an alternative solution, if you think about this problem, and if you take a few minutes to think about it before I give you this, okay, you may consider, changing the weights. So basically, you have first, you say, okay, at this location, xi, whatever, I'm going to learn these shared weights right here. So I'm going to actually do it in this way, so you guys can know that this is weight I for location I. So, and then I'm going to learn a completely different mapping for a different location, wj. All right, so for this wj right here, for this xj, we're going to learn a different mapping. All right, so this is also problematic. Why is it problematic? So we have diversity here. So we have diversity of mappings. So the good news, we have diversity of rules or mappings applied to the input data to X, right? So we do have some diversity, which means, well, if this filter may capture that this is actually, an object that is different from a cat, and here this is part of the cat, right? Based on this distribution, based on this mapping. So we're mapping things differently, not in exactly the same way, but we still satisfy the locality. So we treat everybody, nearby similarly. So we satisfy somehow the locality, and we introduce some diversity. Now, I want you to take a few seconds and think about what is the main drawback of this there are a few drawbacks. Of course, the deeper you think, the more things, like will emerge. But let's find a very a clear, kind of a starking drawback of this approach, of such approach. So think about transforming the image. If you transform or shift the image, what happens? Now the cat will be right here, okay? So now this filter will learn how to basically identify, that was used to identify the chair, now needs to relearn everything, relearn all these weights, okay, to identify the cat. So when we transform things, it doesn't work out well. So shifting and transforming is not good for this network, okay? So let's think about something else. So here we are, varying the relationship between these two. So it means, we have decreased, of course, compared to the fully connected network. This network is cheaper in terms of computational resources because at least we're learning the same mapping for, a neighborhood of pixels. But it is more expensive. It is more expensive than what? Than the fully shared weight. Because now, instead of learning one W for everybody, we're learning different, WIs for every single pixel in the image, okay? For every single local neighborhood. So for each local neighborhood, you sweep the image. So you move, whoops. You move, this quadrant left and right, and then you're going to end up with completely different mapping. So that's not happy news, okay? So there's different things here. First, that shifting, transforming the image may be problematic. It is computationally expensive. So this is not a good idea, all right? It doesn't solve the problem very well. So let's go back to our original problem. So we started with sharing weights. We said that sharing weights is reductionist. It limits the capacity of the network. So we thought about varying weights, but varying the weights at each position of the image. And then, so here in this case, basically, the issues that, as I mentioned, it has several issues that the transformation depends on the input or the pixel position I. So it is position invariant. So here, so it's position, variant. So it varies with the position. So which presents one of the biggest issues right here. Okay. So so we have seen that applying different filters at different locations is not very good because it becomes position variant, and it means that every time we have multiple training samples, right, with different colors, different distributions. So imagine you have multiple cats here, and these cats have different locations. They're translated. You have different types of, images with and without cats. And you want to learn how to identify or recognize if there is a cat in the image at the testing stage. So here we have first, as we mentioned, that there is when we apply a single filter. So let's use a pink color here. So when we apply a single transformation or a single filter identically to all locations, no need to relearn for every pixel. Okay, so we don't need to relearn for every single pixel because here we're learning the same weights for all shared pixels, as I mentioned. So all shared pixels right here will have, will have the same weight. So this is, for example, oops, a bit slow, sorry guys. So this is for this position, then this one is for another position. So I'm learning basically the same mapping for at each pixel in the image. So we don't need to relearn. It's the same guy. It's the same W, right? Same mapping W. Okay, cool. Now, there is one thing here that, as I mentioned, there is an issue with that, is that it is reductionist. So let's remember. So it's reductionist, and it limits which means limits the learning capacity of the network, learning capacity of the network, okay? Now, alternatively, we thought about varying the W, which means with the location, but it turns out not to be a good solution. So here is another idea. So the idea is that we will use multiple mappings or multiple, we call them kernels, okay? So we'll introduce kernels in a bit, but let's say we have a mapping W1 right here. So the pink mapping, and we will apply W1 to all these guys. Okay, so here, W1, and we're gonna go over all this, you know, the image pixel by pixel, and do the, apply the same mapping that we will learn. Of course, W1 is learnable here, so we're learning the W1. And instead of varying the W with the location, what we're gonna add a second W. So here we're gonna have a second mapping, W2, and this will have completely different values. So here we have these inputs, we apply them, we input them to a different, you know, mapping function, W2, and this mapping function, so W2, if we have here 4 values, let's call it W21, W22, 23, W24, and we have the W1, which is equal to 4 elements here. If we take this example, 1, 1, 1, 2, 1, 3, 1, 4. Now what happens is that these two are actually different. So they will increase the capacity of the network. Why is that? Because we are learning different ways. We're learning different ways of transforming, okay, or mapping the input data. So which means maybe this filter will be good, you know, to detect, you know, this part of the image, okay, but not the other part. So what we're doing, we're actually applying multiple filters, and we're hoping by learning the values inside these, you know, filters or these functions right here, these ways, we can get a good prediction at the end, okay? So this is only a single layer. So think about it. I can add also another, you know, mapping right here. So I will choose, for example, color blue, and here we call it W3. And as we increase the number of learned mappings locally, okay, what happens is that somehow through this, you know, through these different kernels or different mappings, I can capture complex patterns in the image. So I'm not basically applying the same, you know, transformation everywhere. I'm applying a bunch of transformations, and what I'm hoping that if I take all these transformations together, okay, maybe I sum them up. Here I can do a summation. So I sum the weights. So I take this weight plus this one and the other one. So I'm gonna get what we call a W bar, an average. And this average is actually a holistic or more kind of universal, or it's kind of a diverse also mapping, local mapping of xi and its neighbors. So this is exactly the idea of channels in convolutional neural networks, and we're going to see them. So basically, this is called you know, channel 1. We have channel 2, and here we have channel 3. So it's a multi-channel kind of convolution, and we can vary the kernels along these channels, so we can have multiple kernels or multiple local mappings that we apply to the image. And we hope that if we learn these weights very well, if we learn them very well, the average will give us a more kind of universal representation of this object. So basically it will learn the patterns, the local patterns that allow us to identify or recognize a cat. Okay, so it will, and remember guys, as I mentioned earlier, so here I'm only talking about weights, but there are more things. Of course, when you do the weights, then you need to add some bias, and then you go through activation, and this is exactly similar to an MLP or a fully connected network. Okay, cool. So now I think this idea is clear. This turns out to be a good solution. Maybe you guys can think about a better solution than this one, but that's something you can ponder over after the lecture. So before we go ahead, I would like to introduce the family of what we call convolution operations. So here, actually, this filter happens to be a kernel weight matrix, or we call it also filter. And this operation right here is a convolution operation. So we convolve these, pixels with this weight, and a convolution is a simple mathematical operation where we do element-wise multiplication. So we multiply the values of this weight, with these pixel values one by one, element-wise, and we do a summation. So we sum, and then we get the final output value of this convolution. Okay, so this is called a convolution, and this is how we are applying the mapping. So the mapping here is convolving the image, the input, okay, with a kernel. All right, a kernel, let's call it W, for example, W1, if it's the pink one here, or W2 if it's the orange one. All right, now, so the convolutions have different properties. So when you do basically convolutions, we're going to see each one of those in a bit in detail. But right now, I want just to give you an overview of the different operations that you need to think about when you're using this convolution. So first is the size of the filter. So here, the size of the filter is the dimension of the kernel. So the kernel here is a two-dimensional kernel. For example, it's 2 by 2. This one is 4 by 4. So the size of the kernel is important as a hyperparameter. How are you going to fix the size of the kernel? The second thing is that sometimes when you want to do a convolution, so if I duplicate this, okay, so the pixels at the edge are problematic because you can start here, but you cannot, basically look at this pixel at the edge. You're starting here, but you're missing out this first pixel. Okay, so that should be kind of centered. So the idea is that to kind of cover the edge pixels, the pixels at the edge, we will use what we call a padding operation. So what padding does is that it takes, the edge pixels and it adds 0. So this is, for example, a 1 padding. So 1 padding, we added a 0 to the right, left and right of the image, top and also below the image. And we have immersed literally the image in darkness. So we have lots of zeros. So if you do 2 padding, it means, you add 2 zeros. So the image size will increase by 2 times P. P is the size of the padding, okay? So now there is a third element, which is what we call the stride. So what is a stride? So the stride, when you take this, when you apply the filter or the kernel, you do the convolution, you're gonna move your kernel by 1 pixel. So if I move it by 1 pixel, that's the stride. So that's the step at which I'm moving my kernel or sweeping my kernel along the image, right? So here, if we take a stride of 1, so it means s equals 1, you do, you take a step of 1. If you do, for example, 2, you're going to skip, 2 pixels. So I take, these 2 pixels, and then I'm going to skip to 1, 2, and then apply my kernel, 1, 2, apply my kernel, etc. So I'm covering more here quickly because I am, striding at 2 horizontally and vertically, and that will basically decrease the number of operations. But also you can think about this as a zooming effect. So instead of looking at each single pixel in the image, I'm just looking overall and trying to capture something interesting here at this stride. So it kind of increases my my field of view because I'm covering less, but I'm covering sparser kind of, locations, okay? So there is also what we call dilation, and dilation is it's very simple actually. So here, dilation, if you take a 2 by 2 kernel, we will insert zeros. If I do a dilation of 1, it means I'm going to increase the size by 1. So I have 3 by 3. And in the 3 by 3, I'm going to put zeros everywhere right here. So this becomes literally dark. So this doesn't influence my my mapping because I am masking all these pixels in between. So what happens when I dilate my kernel and with one step? So here, all these pixels will not contribute to the learned mapping because they will become unseen by my convolution, by my dilated convolution. Okay, so I'm just kind of spreading out my my vision and looking around and ignoring what's inside, looking at the corners. Okay, so basically the dilation rate here is defined as the number of zeros we intersperse between the weights, as I explained right here. Okay, so this increases, of course, the kernel size, and it introduces what we call sparsity, which means in this 3 by 3 now current dilated kernel matrix, we have lots of zeros. So because we have lots of zeros, my kernel or my mapping becomes sparse. All right, so which means many connections in the network, remember the connections in the network, they will disappear. Okay. Disappear. All right. So I think this is a kind of the whole story of motivating CNNs, how we started from FCNs. They have different issues. We try to solve each issue one by one, right? Proposing different solutions or sub-solutions and criticizing the solutions until we got to the final stage where we had this multi-channel kind of weight-based, localized convolutional neural networks. And with these, I think, while varying the size, doing some padding, varying the stride, varying the dilations, we can capture different patterns, and we can learn different patterns in the data and allow for a classification or a distinction between, for example, an image of a cat and an image that doesn't have a cat. Okay, cool.